Hello, my name is Hannah Krehbiel. I'm a junior here at the University of Arkansas at Little Rock, and today I'll be presenting my research on the application of ionic materials in organic solar cells. So, as fossil fuels continue to be depleted, we need to turn to more sustainable methods of obtaining energy. So, good example of this is solar energy. And we are specifically looking at dye-sensitized solar cells, which work by effectively mirroring the mechanism of photosynthesis, as can be seen here in this diagram. Dye-sensitized solar cells show several advantages over current silicon models, including being more flexible and having less toxic and costly syntheses. However, they still are exhibiting a lower power conversion efficiency. So until that increases, it's difficult for them to be widely available commercially. So we wanted to make a novel dye pair that could be used for a dye-sensitized solar cell. So we used a single-step ion exchange method where we combined our donor material here, fluorescing sodium, with our acceptor material, Victoria Blue B. So we dissolved each in their respective solvents, allowed them to stir over 48 hours and combine. And then we are able to remove the counter ions, which have formed a salt in the water layer, remove that. We're left with our ionic material and dichloromethane, which we can rotovap to evaporate the DCM and then freeze dry to remove water. And then we're left with our material to characterize. So we want to generate a dye pair that exhibits FRET, which is force to resonance energy transfer. So non-radiative form of energy transfer, in which energy from the emission of a donor material is transferred to the absorption of an acceptor material, which in turn increases our acceptor's emission. And so dye pairs that exhibit FRET have been shown to lead to increased power conversion efficiencies in dye-sensitized solar cells. But in order for FRET to occur, a few requirements have to be met. There has to be significant overlap between donor emission here and acceptor absorbance, which is this J integral value. And the distance between the donor and acceptor material have to be less than 10 nanometers in order for the energy to be transferred. And so after we synthesized this material, we wanted to characterize it photophysically to see if it was exhibiting FRET or if it would work well in solar cells. So we characterized it using absorbance and emission. So here for our absorbance graphs, we can see that we have an increase in absorbance from our parent materials to our combined, both at 5 micromolar and here with 10 micromolar. And so that's one good sign. And then here for our emission, we see that sorry, for here and right here for our emission, we can see that it's actually decreasing from the parent to combined. This is a good indicator that FRET is occurring because energy has to be transferred from the parent compound, the donor material, to the acceptor in order for FRET to occur. And then we wanted to synthesize nanoparticles as they can be used in a wide variety of applications. So we reprecipitated the ionic material in water under sonication to break them down into nanoparticles. So here we have our emission of our nanoparticle. We can see that it retained its peak at a lower concentration. As we increase the concentration, however, the fluorescence goes down, which just has to do with the fact that it could be aggregating or quenching. So in order to determine if our material was indeed exhibiting FRET, we looked and conducted some of these calculations here. So we have our maximum molar extinction coefficient, which we obtained from our absorbance graphs. Here we have our calculation of J integral, which is this overlap between emission of the donor and absorbance of the acceptor. So we see that that's to the 15th power, which is a high number. It's a good indicator that FRET is occurring. And then our theoretical FRET distance here was within 10 nanometers. We calculated it to be 5.46. So that shows that FRET could indeed be occurring. So in summary, our ionic material shows promising photophysical characteristics. However, when we conducted cyclic photometry, we decided that it may be better suited for a different application because in order for it to be used in a solar cell, it has to have high oxidation and reduction potentials, which it has not shown so far. However, it is showing broad absorption, which is good for higher efficiencies in solar cells as it could absorb at different wavelengths of light. But in the future, we hope to continue to characterize it and then change the counterion in order to explore future dye pairs and then synthesize and characterize those. So I would like to thank the Siraj Research Group and INBRI and the NSF for funding our work. We'd like to thank Dr. Mustafa El Said at Georgia Tech for allowing us to learn and conduct research in their facilities, our Center for Integrative Nanotechnology for the use of their equipment, and Signature Experience Award for funding this work. I would also like to thank the Arkansas State Legislature for allowing us to present our work to them. I hope that you enjoyed this and hope that you all are doing well. Thank you so much.